All right, let's jump right in. We're tackling a massive question today. How does your brain make sense of a world that is constantly throwing messy, incomplete, and just plain uncertain information at it? Let's figure it out.
I mean, really think about it for a second. You're in a loud room, trying to have a conversation, or you're trying to read a blurry sign from far away. Maybe you see a weird shape in the shadows. The truth is, your senses almost never get a perfect, crystal clear signal. So how in the world do we go from all that chaos to, well, this, a coherent, stable reality? That's the puzzle we're going to piece together today.
Okay, so here's our game plan. First, we'll unpack what we're calling the perception puzzle. Then, we'll introduce this really cool idea of your brain as a detective. After that, we'll look at a simple test scientists use to see this in action, check out the models they build from it, and finally, wrap it all up with why any of this actually matters.
All right, let's kick things off with section 1, the perception puzzle. And the key thing to get here is that seeing isn't just a passive thing, like a camera recording. It's an active process of construction.
You see, what's so crucial to understand is that your brain isn't just a passive video camera, recording whatever's out there. Nope, it's constantly being fed this fuzzy, partial data. Your eyes, your ears, they're just the first step. They're the microphones and lenses. The real magic, the part where it all gets interpreted and makes sense, that happens inside your head. So if your brain isn't a camera, then what is it? Well, this brings us to a really powerful idea. What if your brain is more like a detective? This is the absolute core of a theory that scientists call the Bayesian brain.
Now, the main tool this detective uses is something called Bayesian inference. And I know, that sounds super technical, but don't let the name scare you off. At its heart, it's actually a beautifully simple and logical way to update what you believe. You just start with what you already think is true, you get some new piece of evidence, and you combine the two to land on a better, more informed conclusion. That's it.
This quote from the research just nails it perfectly. The human mind operates like a capable data scientist or crime scene investigator when dealing with noisy and ambiguous data. It's not just guessing wildly, right? It's systematically weighing the evidence, just like a detective at a crime scene trying to piece together what really happened from a bunch of limited clues. And this is basically the detective's method in action. First, the detective has a hunch, right? A theory. That's your prior belief. For your brain, that's all your past experience, all your knowledge about how the world generally works. Then, a new clue turns up at the scene. That's the new evidence coming in from your senses. And finally, the detective updates their theory of the crime. That's your new, updated belief about what you're actually seeing or hearing. And this cycle, it's happening constantly, thousands of times a second, without you even noticing. Okay, that all sounds great in theory, but how do scientists actually prove this? How do they see this little detective at work inside our heads? Well, they use a classic, super clever experiment. It's called the Two Alternative Force Choice Task, or just 2AFC for short. And it's incredibly simple, but also incredibly powerful. Just imagine you're looking at a screen with a faint pattern of dots, and you have to decide, are they moving left or are they moving right? There's no obvious answer. It's ambiguous, and that makes it the perfect crime scene to watch the brain's decision-making process when it's really under pressure. So why this specific task? Well, because it's a super clean, controlled environment. It strips away all the extra distracting noise and lets researchers focus purely on that moment of decision. They can precisely control how good or bad the evidence is, like how faint the dots are, and see exactly how people respond. This lets them build and test really precise mathematical models of what's going on in the brain.
Okay, so once the scientists have all this data from the tests, they need to explain it. Let's dive into the investigators' toolkit and look at the theories they use.
So you've got two big players here, signal detection theory, or SDT, and Bayesian decision theory, BDT. Let's break them down. SDT basically says your brain just listens for the loudest signal. Whichever option, left or right, shouts the loudest through all the internal static in your brain, that's the one you pick. Simple. But BDT, the Bayesian theory, argues it's a bit more sophisticated than that. It says you don't just listen for the loudest signal. You also factor in what you expected to see or hear in the first place. You use your prior beliefs.
In this Bayesian approach, this idea of combining evidence with expectation leads to some really fascinating, almost weird predictions that the simpler models just can't explain. And one of the coolest is something called a bimodal response. So what in the world does bimodal even mean? Well, normally, if you ask a bunch of people to guess something, you'd expect their answers to cluster around a single average, right? One big pile in the middle. But in some of these tasks, the guesses form two completely separate piles, two peaks. This tends to happen when your prior belief,
Let's say your brain's assumption that most lines are either vertical or horizontal is just as strong as the new evidence from your eyes, which might be telling you the line is tilted at a 45-degree angle. Your brain can't easily decide which to trust, the prior or the evidence, so it kind of hedges its bets, producing two distinct clusters of answers. It's a huge clue that the brain really is mixing priors and evidence, just like the detective.
Okay, so we've looked at the puzzle, the theory of the brain as detective, and the evidence from the lab. Now let's bring it all home and get to the verdict. Why is this view of the brain so important? Why does it matter?
Well, the implications here are actually huge. For starters, this model helps explain all sorts of things, like how you can seamlessly combine what you see with what you hear to pinpoint exactly where a sound is coming from. It gives scientists a real mathematical framework for understanding uncertainty in the brain. And get this, these exact same principles are being used to build smarter AI that can actually navigate the messy, unpredictable real world. But maybe most profoundly, it completely changes how we think about perception itself. It suggests that what we experience isn't a true, perfect window onto reality, but is instead your brain's constantly updated best guess of what's out there. And that leaves us with one final kind of mind-bending question to chew on. If everything you see, hear, and feel is just your brain's best guess, a conclusion reached by a detective using incomplete clues and past experiences, then what is reality really? Something to think about. Thanks for tuning in.